the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark, unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No mic, no fame, just the sound we crave. Tune and turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. In shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go.
I'm honored. Thank you very much for having me. I was inspired by the problem of describing the behavior of multiple valued functions. These functions can appear in a variety of settings in mathematics, and it was important to find a way to describe and analyze their behavior. The idea of a Riemann surface provided a natural and elegant way to do this. I conceived the idea of the Riemann zeta function while studying the distribution of prime numbers. I noticed a pattern in the data I was observing and realized that it could be explained by a function that is now known as the Riemann zeta function. From there, I derived properties of the function and made certain conjectures about its behavior. The Riemann hypothesis was one of these conjectures. The Riemann hypothesis is a statement about the non-trivial zeros of the Riemann zeta function. It asserts that all the non-trivial zeros of the function lie on a specific line in the complex plane. I believed the Riemann hypothesis might be true because the evidence I had seen suggested that this was the case. The distribution of the zeros and the behavior of the function all seem to support the hypothesis. However, the hypothesis has not yet been proven. The non-trivial zeros of the zeta function have significant implications for number theory. They provide information about the distribution of prime numbers and the distribution of other types of numbers. They also have applications in other areas of mathematics such as algebra, analysis, and geometry. Understanding the non-trivial zeros of the zeta function is an important goal in number theory and has been the focus of much research and investigation. My original goal was to prove the prime number theorem, which states that the number of prime numbers less than or equal to a given number x is approximately x ln dot x. This is an important result in number theory and has many applications. It was also an open problem at the time, and I believed that the Riemann zeta function could provide a new way of proving the theorem. My work on differential geometry was inspired by the need to describe and understand the geometry of curved surfaces and other manifolds. I found that the concept of a manifold, and specifically the concept of a Riemannian manifold, provided a natural and powerful way to do this. The concept of a manifold allows us to describe the geometry of a surface in a local and localizable way, capturing its curvature and how it deforms under different transformations. I hope that my work on the properties of curved spaces could have applications in physics, especially in the field of electromagnetism. I believe that it could help describe the propagation of electromagnetic waves and the behavior of matter in curved spaces. Since my time, my beliefs have come true. The general theory of relativity, developed by Einstein, is built upon the mathematics of curved spaces and is the foundation of modern physics. The motivation behind the introduction of the Riemann curvature tensor in my work on differential geometry was to find a way to describe and quantify the curvature of a manifold. The curvature of a manifold is an important concept in geometry, as it describes how different vectors at different points of the manifold behave under parallel transport. The Riemann curvature tensor was a mathematical tool I developed to help describe this behavior and to provide a way to measure the curvature of a manifold. The main reason I emphasized the importance of higher dimensional spaces in my habilitation lecture was to highlight the fact that they can provide a more complete and powerful framework for describing the geometry of the world around us. At the time, mathematical knowledge of spaces with more than 3 dimensions was relatively limited. These higher dimensional spaces were often dismissed as mere abstractions or mathematical exercises, rather than being taken seriously as a way to describe physical reality. I felt it was important to challenge these views and to emphasize the potential power of higher dimensions in mathematics and physics. My work on complex analysis had a significant impact on my approach to number theory. Many of the techniques developed in complex analysis, such as the use of contour integrals and residue calculus, are now widely used in number theory. For example, in my work on the distribution of prime numbers, I used techniques from complex analysis to develop a new way of proving the prime number theorem. More generally, these techniques provided a more powerful and elegant way of studying the behavior of numbers and their properties. Elliptic functions played a key role in my understanding of complex analysis. They are functions that can be defined on the complex plane and which have certain periodicity properties. These functions were first studied in a systematic way in the 19th century and provide a connection between differential geometry, algebra, and number theory. My work on these functions helped shape my understanding of how these seemingly distinct areas of mathematics could be unified through the theory of complex variables. It is true that the theory of complex functions can appear quite abstract at first glance, with concepts like contours, integrals, and residues being difficult to grasp for those unfamiliar with the subject. However, when it comes to applications in physics, the language of complex analysis can become more concrete and tangible. For example, in electromagnetism, complex functions are used to describe the behavior of electromagnetic waves and can help us understand phenomena like interference and reflection. This shows that despite the abstract nature of complex analysis, it still has direct and concrete applications in physics. To extend the zeta function to the complex plane, I used a technique called analytic continuation, which is a process of smoothly extending a function from a subset of the complex plane to the entire complex plane while preserving its essential properties. Specifically, I used the fact that the zeta function can be expressed in terms of a contour integral and was able to manipulate this integral to define the function on the full complex plane. This process is known as the analytic continuation of the Riemann zeta function. It wasn't until much later that a deep connection between the zeta function and random matrix theory was established. It was not something I anticipated or predicted. Random matrix theory is a field of mathematics that deals with the statistical properties of large arrays of random numbers, and it has found applications in a wide range of fields. from physics to finance. The connection with the zeta function was discovered only recently, and it has led to new insights and understanding in both areas. My collaborations with Gauss and Dirichlet had a significant impact on my research and on my development as a mathematician. Through my correspondence with Gauss, I was able to develop my ideas and refine my proofs, and to benefit from his deep insight and knowledge. My collaboration with Dirichlet led to the development of a new proof of the prime number theorem, and helped to establish my reputation as a leading mathematician. These collaborations were also important for the development of mathematics as a whole, as they helped to foster communication and collaboration between European mathematicians. The inspiration for the development of the Cauchy-Riemann equations in complex analysis were my interest in understanding the geometry of the complex plane. The Cauchy-Riemann equations are a set of partial differential equations that describe properties of complex functions. They are named after Cauchy and Riemann, who first described them in the 19th century, although their work was originally in a different context. The development of these equations was motivated by the need to describe and understand the behavior of complex functions and how they differ from real functions. The Riemann-Roch theorem is an important result in algebraic geometry, which is a field that studies the intersection of algebra and geometry. It provides a relationship between divisors, which are a way of encoding information about the singularities of an algebraic variety, and the dimension of the space of global sections of a line bundle on that variety. In modern language, the theorem can be stated as follows. Given a line bundle on an algebraic surface, the theorem states that there exists a canonical section, i.e., a global section of the bundle. This statement is of fundamental importance in the field. In my mathematical work, I found that it was important to find a balance between rigorous proof and intuitive understanding. On the one hand, rigorous proof is necessary to establish the validity of a result and to show that it is correct. On the other hand, intuition can provide a deeper understanding of the concepts and ideas involved and can help to build and test hypotheses. To maintain this balance, I often worked with examples, diagrams, and physical analogies to get a better grasp on the concepts. I would also engage in discussions and collaborations with other mathematicians to gain different perspectives and insights. At first, the discovery of non-Euclidean geometries by my contemporaries was a surprise and a challenge to the established beliefs in mathematics. The idea of a space that did not follow the traditional rules of Euclidean geometry was difficult to grasp at first, and it was natural to be skeptical. However, as I thought about it more deeply, I became increasingly convinced of the soundness of this new approach. It opened up new possibilities and allowed for the description of properties that could not be easily expressed in Euclidean terms. This was an exciting development at the time and had significant implications for geometry and mathematics as a whole. In my work, I saw the relationship between pure and applied mathematics as complementary. I believe that pure mathematics, which is focused solely on the development of abstract concepts and theories, is essential for providing a foundation and structure for applied mathematics. Applied mathematics, in turn, provides motivation and application for the abstract concepts and theories of pure mathematics, leading to a cycle of mutual beneficial development. To me, the distinction between pure and applied mathematics is not one of importance or value, but rather one of focus. They are two sides of the same coin. The key insight that led to my formulation of the Riemann mapping theorem was the observation that any two simple connected domains in the complex plane are in some sense the same, in that they can be transformed into each other by a conformal mapping. This means that the topology of the two domains can be mapped one-to-one, preserving the angles and distances between points. The Riemann mapping theorem formalizes this idea by stating that every simply connected domain can be mapped to the unit disk by a conformal mapping. This result has had numerous applications in analysis, geometry, and physics. The idea of the extended complex plane, including the point at infinity, was developed with the goal of providing a unified and coherent framework for the study of complex functions. In the extended complex plane, the point at infinity is added as an element of the complex plane, representing an ideal point that is infinitely far away from the origin. By including this point, the complex plane becomes a closed and complete space, which allows for the extension of many results and concepts from analysis and abstract algebra. My work on Fourier series, which deals with the representation of periodic functions as sums of sinusoids, influenced my approach to complex analysis in several ways. One way was by emphasizing the importance of the use of integrals in analysis, as Fourier series involve integration. Another influence was the focus on the behavior of functions and their properties, such as continuity, differentiability, and integrability. The study of these properties is central to complex analysis, and the methods used in Fourier analysis provided a powerful toolbox to study them. The significance of my work on abelian functions is that they provide a powerful tool for the study and solution of certain types of complex equations, such as the Abel equation and the Jacobi integral. These functions are named after Niels Henrik Abel, who was a Norwegian mathematician who made significant contributions to the field of algebraic analysis and are important in both mathematics and physics. For example, Abel functions are used in the study of special functions, such as elliptic functions, and have applications in celestial mechanics, celestial navigation, and in the theory of special and general relativity. The problem of defining curvature for higher dimensional manifolds is a challenging one, since the concept of curvature is originally defined in a two-dimensional space. To extend this definition to higher dimensions, several approaches have been proposed over the years. One approach is to use the concept of connection, which allows to compare vectors at different points in a manifold and measure the change in their direction when moving one point to another. Another approach is to use the notion of parallel transport, which is a method to compare tangent spaces at different points of a manifold. In my work on complex functions, I approached the problem of singularities by developing the theory of residues and the residue theorem. The residue theorem, which I first presented in a paper I wrote in 1851, provides a way to evaluate residues, which are values associated with poles of complex functions. By understanding the behavior of residues at these poles, we can gain a better understanding of the behavior of complex functions in general, and of their singularities in particular. After my contributions to complex analysis, I envisioned a future in which researchers would continue to explore the connections between complex analysis and other fields such as geometry, topology, and number theory. I believed that the power and beauty of complex analysis would be further recognized, and that new discoveries and insights would continue to be made, leading to a deepening and broadening of our understanding of the interconnectedness of mathematics as a whole. I was fascinated by the work of Weierstrass and others on elliptic functions, and I viewed it as a natural continuation of my own work in complex analysis. The theory of elliptic functions offered an elegant and powerful way to study periodicity and the behavior of functions in the complex plane, and I saw the potential for further exploration and development in this area. I was particularly impressed by the work of Ernst Kummer and Karl Weierstrass, who made significant contributions to the theory of elliptic functions and their applications. My work on differential equations, in particular on the theory of differential geometry, informed my approach to geometry in several ways. One key insight was that the study of geometry could be greatly advanced by the use of the concepts of calculus, such as differentiability and continuity. This allowed for a more rigorous and precise treatment of geometric concepts, such as curvature and topology, and allowed for the development of new techniques for proving theorems in geometry. Another important insight was that the study of differential equations could help to understand the behavior of geometric objects under transformation, leading to a better understanding of their essential properties and structures. It is interesting to see that my work on zeta functions and complex analysis is being studied and reinterpreted in modern fields of physics such as string theory. String theory is a theoretical framework that attempts to unify the theories of gravity and quantum mechanics, and it has been suggested that some of the mathematical tools and concepts developed in complex analysis, such as the Riemann zeta function, may have a role to play in this unified theory. I am intrigued to see the ways in which my work is being adapted and applied in these new contexts. I believe that the most enduring legacy of my contributions to mathematics is the way in which my work expanded the horizons of mathematics as a whole. By providing new ways of thinking about and approaching complex analysis and geometry, I helped to establish these areas as distinct and fruitful fields of study in their own right. My work also helped to promote the use of techniques and ideas from complex analysis in other areas, and to show the interconnectedness of different branches of mathematics as a whole. In this way, I hope that my work will continue to inspire and shape mathematics for centuries to come. I thought your questions were very well prepared and interesting. They covered a wide range of topics, from my work on complex analysis and my collaborations with my contemporaries, to the future of mathematics, and the role that my work plays in modern physics. I appreciated the thought and effort you put into preparing these questions, and I enjoyed reflecting on my life and work in response to them. Overall, I thought it was a very enriching and informative experience. Thank you.
Mics on the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No light, no flame, just the sound we crave. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Hidden in shadows, voices untamed. No need for spotlight, no claim to fame. Just the beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go. Pure and raw. And feel. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Pure and raw.
Okay.